Today we're going to derive some rules to make finding the derivative a little bit easier than using the definition. And the first rule we're going to look at is called the constant rule. Remember, we always start with our definition, which is the derivative is the limit as h approaches 0 of f of x plus h minus f of x all over h. So for the constant rule, we're going to let f of x be equal to some constant c. Well, since that's a constant and there is no variable to substitute in for x, well, f of x plus h is also c. So when I take the limit as h approaches 0 of f of x plus h, we end up with c minus c over h. So in the end, that's 0. That is the constant rule. If c is a real number, the derivative of c, of any constant value, is f prime of x. That's equal to 0. Or, in Leibniz notation, dy dx is equal to 0. The derivative of any constant is 0. If you think of that as a function, if my function is a constant, that's like a horizontal line. So let's say that's y is equal to 5. Well, we know a horizontal line has a slope of 0, which is basically what the derivative is. So it all kind of ties into what we are used to. The power rule is a tiny bit more complicated to derive. We're going to start, but once we use it, once we come up with the rule, it's pretty handy. So we're going to start with a function that has a coefficient, and my variable is x, so it's c times x, and x is raised to the nth power. That means f of x plus h is going to be my constant c, my coefficient c, times the quantity x plus h raised to the nth power. So if I substitute into my definition, I have f of x plus h is c times the quantity x plus h to the nth power minus c times x to the nth power all over h. I'm going to factor out that coefficient of c. So he's just going to hang out in front, and then I have x plus h to the nth power minus x to the nth power all over h. Well, what has to happen is I have to figure out how to expand this thing. And to expand the binomial, you would actually use the binomial theorem that you learned last year. I don't expect you to remember that right now, but that's where that expansion is going to come from. So the binomial theorem, if I'm going to expand x plus h to the nth power, it looks like this. My first term, if I were to multiply all the first terms, I would end up with x to the n. My second term ends up being the coefficient in front is actually going to be the exponent, and then my x starts stepping down in power, and my h starts stepping up in power. Plus, and then you have everything in the middle, till finally my last term is h to the n. If I'm going to put that, expression in for x plus h to the n. And again, it's a little nutty, but that's where this comes from. I have my limit, I have my constant c, and then I have x to the n plus n times x to the n minus 1 times h. The pattern's going to continue until the very last term is h to the n. All of that minus an x to the n. All over h. So let's just look and see what this is. My x to the n is going to subtract away. Every other term in here has at least one h as a product or as a factor of it. So in the end, these are going to subtract. I'm going to be able to factor an h out of every single term, and then when I evaluate it as h approaches 0, the only thing left is going to be this guy right here. Is going to be n times x to the n minus 1, because he's dividing away. Everything else will have a 0, will go to 0, and that's what you're left with. So, if c is a real number and n is a rational number, then if I'm given this function, the product rule is this: f prime of x is going to be the coefficient times the exponent times the variable raised to the n minus first power. Oh, I got to write smaller so you can see it. And that's the power rule, and it makes it a lot easier to find the definition. One more time, f prime of x is going to be c, the coefficient, times the exponent, times the variable, and then you're dropping the exponent by 1. You bring the power down in front, and you reduce it by 1. That's the power rule. Next is deriving the sum and difference rule. If I start with a function, f of x, and that's equal to the sum of two separate functions, if I take the limit, if I use the definition, f prime of x is going to be the limit as h approaches 0 of f of x plus h, which is going to be u of x plus h plus v of x plus h minus u of x plus v of x all over h. That's the definition. And all I'm going to do is rearrange the terms and write them separately, because I can regroup. I can group my u's together and my v's together. And I can put each one of those over h, and I can break up the limits. So doing that, I end up with the limit as h approaches 0 of u of x plus h minus u of x all over h. Using my limit laws, that's also plus the limit as h approaches 0 of v of x plus h minus v of x all over h. So by definition, this is u prime of x. And by definition, this is v prime of x. So basically, the derivative of a sum is equal to the sum of the derivatives. So given u of x and v of x, and the sum u of x plus v of x, then f prime is going to be u prime plus v prime. And that's the same for subtraction. All I would do for the difference instead of the sum is this would be subtraction. You would still regroup, and you would still have the same typical answer. So here's how we use these rules to make finding the derivative much easier. If I have f of x, and this guy is slightly complicated, x to the 5th, 6x squared, minus 10x, that would be a real pain in the rear to find f of x plus h raised to the 5th power. I don't have to do that anymore. I have the power rule. So f prime of x ends up being this: 5x to the 4th plus 12x minus 10. Here's why. I bring the exponent down in front, and I lower it by 1. So 5x to the 4th, my exponent down in front, multiplied by the 6 to get the 12. 2 minus 1 is 1. And then here, my exponent is 1, it's implied, and x to the 0 is an implied 1, so you don't see the x anymore. So that is the derivative of f of x. Now we call f prime of x and dy dx the first derivative, but I can take as many derivatives as my function allows. So quite often we find the first and the second derivative. The second derivative is found by doing the same thing again, taking the derivative of f prime of x, or dy dx. So to finish this, and then we'll work more examples in class, if I want to find the first and second derivatives of y equals x cubed minus 5x squared plus 2, my first derivative would be dy dx. and that's going to be 3x squared minus 10x. Remember, this is a constant, and the derivative of a constant is 0. Now the second derivative looks like this, d squared y over dx squared. And we just do the same thing again. It ends up being 6x minus 10. I could find the third derivative, which ends up being 6, and the fourth derivative, which would end up being 0. I keep going until I end up with a 0. Now, notation, instead of dy dx, we could also say f prime of x. So the second derivative would be f double prime of x. And we'll work more examples in class to get you a better idea of how to use these new rules instead of the definition of the derivative.